equation y equals f of x represents the absolute value function. In this case, f of x means the absolute value of x. Now let's look at two different functions, y equals 2 times the absolute value of x and y equals the absolute value of 2x. If we graph both functions on the xy coordinate plane, we'll notice something interesting. The graphs are exactly the same. No matter what x value we plug in, both functions give us the same y value. So here's the question: why are there two different expressions for the same graph? What's the difference between them? Let's rewrite them using function notation. Y equals 2 times the absolute value of x can be written as y equals 2 times f of x, and y equals the absolute value of 2x can be written as y equals f of 2x. Now let's talk about what these forms mean. In y equals 2 times f of x, the x values stay the same, but the y values are multiplied by 2. This is called a vertical stretch. In y equals f of 2x, the y values stay the same, but the x values are multiplied by 2. This causes a horizontal compression. In other words, the graph is squeezed toward the y-axis. So even though both graphs look exactly the same, they come from different kinds of transformations. One stretches the graph vertically, and the other compresses it horizontally. In other words, a vertical stretch by a factor of a and a horizontal compression by 1 over a can result in the same graph. That's why we can write the same graph in two different ways, each one showing a different transformation. Even though these transformations create the same final graph, the way individual points move is very different. Let's start with the original function. Y equals the absolute value of x. Suppose we look at the point open parenthesis, 1, 1, close parenthesis. Under the transformation y equals 2 times f of x, this point becomes open parenthesis, 1, 2, close parenthesis. Here, the x value stays the same, but the y value is multiplied by 2. Now, let's check the other case, y equals f of 2x. The same original point, open parenthesis, 1, 1, close parenthesis, is transformed into open parenthesis, 1/2, 1, close parenthesis. This time, the y value stays the same, but the x value is divided by 2. So even though both transformations produce graphs with the same overall shape, the actual movement of each point is very different. One stretches the graph vertically, and the other compresses it horizontally. Every function begins with its conditions, especially the domain and the range. Let's think of a real-world example. Imagine you're an architect creating a design formula. Suppose the x-axis represents the width of the road, and the y-axis represents the height of an overpass. If the road width cannot be changed because of legal restrictions, then the x values must remain fixed. In that case, you would adjust the y values with a new function and run your simulation accordingly. Now let's take a different situation. Imagine analyzing the trajectory of a projectile. To avoid being detected by enemy radar, the height or y value must stay the same. Instead, you would adjust the x values in your simulation. That is exactly why we study vertical stretches and compressions and horizontal stretches and compressions. These transformations help us understand how changing the domain or the range of a function affects the entire model in real-world applications. Let's try to understand this more precisely using an equation. Suppose the original function is y equals f of x. Now imagine that it has been transformed into y equals a times f of k times open parenthesis, x minus d close parenthesis, then minus c. In this situation, we often see 4 types of problems. First, drawing the graph of the transformed function. Second, finding the domain, the range, and specific function values based on the transformation. Third, figuring out how a coordinate point from the original function, for example x, y, is mapped to a new point on the transformed function. And fourth, working backwards. Given a point on the transformed function, we find the original coordinate on the parent function. These are the key skills needed to fully understand function transformations. In a transformed function like y equals a times f of k times open parenthesis, x minus d close parenthesis, then minus c, the expression k times open parenthesis, x minus d close parenthesis represents the change in the x values. Let's isolate that part. We can say that x equals k times open parenthesis x prime minus d close parenthesis. Now let's look at the y side. If we move everything except the f expression to the left side, we get y plus c divided by a equals f of k times open parenthesis x minus d close parenthesis. If we treat that entire expression as y, then we get y equals open parenthesis y prime plus c close parenthesis divided by a. But if we want to keep the transform function in its original form, e prime equals a times y minus c. So now we know how a point transforms. The new x-coordinate, or x prime, is x divided by k plus d, and the new y-coordinate, or y prime, is a times y minus c. This gives us the exact mapping between the original graph and the transformed one. For example, if the function y equals f of x is transformed into y equals 3 times f of 2 times open parenthesis, x minus 1 close parenthesis, then minus 2, then the original point x, y, is mapped to a new point 1/2 times x plus 1, 3 times y minus 2. On the transformed graph, to remember this more simply, just think about how to get back to the original x in the expression. F of k times open parenthesis x minus d close parenthesis. For the part k times x to become the original x, you need to multiply x by 1 divided by k. And for x minus d to become the original x, you need to add d. So the x-coordinate on the transformed graph becomes 1 divided by k times x plus d. The new y-coordinate stays in the form a times y minus c. Let's try practicing this just a couple of times. First example, suppose y equals f of x is transformed into y equals 1/2 times f of 3 times open parenthesis, x minus 1 close parenthesis, then minus 4. Let's figure out the transformation of x and y. To turn 3 times x into the original x, we multiply x by 1/3. And to turn x minus 1 into x, we add 1. So the new x-coordinate is 1/3 times x plus 1. That means a horizontal compression by a factor of 1/3 and a shift to the right by 1 unit. Now for y, it becomes 1/2 times y minus 4. That means a vertical compression by a factor of 1/2 and a shift downward along the y-axis by 4 units. Now a second example. Suppose y equals f of x is transformed into y equals 3 times f of 2x minus 6, then plus 3. Let's factor the expression inside the function. F of 2x minus 6 can be rewritten as f of 2 times open parenthesis x minus 3 close parenthesis. Now let's find the x transformation. To undo the multiplication by 2, we use 1/2. To undo x minus 3, we add 3. That means a horizontal compression by a factor of 1/2 and a shift to the right by 3 units. So the new x-coordinate is 1/2 times x plus 3. As for y, it becomes 3 times y plus 3. That means a vertical stretch by a factor of 3 and a shift upward along the y-axis by 3 units.